Now let's take an example of force and torque on a dipole. Let's take a current loop here, and let's consider a point, a height z above it. And the current loop, by Biot-Savart law, produces a magnetic field B up here at a height z. And for the moment, we're going to just talk about B as having a z component, which is a function of z in the k-hat direction. And now let's put a dipole, and for the moment, let's fix the dipole mu so that dipole moment has a z component also in the k-hat direction. And what we'd like to do is look at the force on that dipole, which we refer to as the gradient of the dipole moment dot B. Well, mu dot B is simply mu z bz here at this point. And in general, so we have the gradient. Now, in general, the gradient has three terms, so we have to be a little bit careful. There's a d by dx of mu z bz plus d by dy of mu z bz plus d by dz of mu z bz. Now, in this case, because this is in the z direction, you might say, is there some type of gradient, some partial derivative of the z component in the x direction? Now, technically, the magnetic fields do have a slight change as we go in the x direction, but we're assuming that is essentially 0. And in the same way, we're assuming that in some y direction, that if we choose I hat, here k hat is into the board, and j hat, k hat is in this direction, then we're also assuming that derivative is essentially 0. So the only non-zero derivative we have is on the z component of the magnetic field. And that's our force in this particular direction. There's some I hat, j. This is all, hang on a second, the I hat component, the j hat component, and the k hat component. Now, let's ask ourselves which way this force is pointing. Well, as we move away from the current loop, the magnetic field component is decreasing the further away you get. So we expect that the partial derivative of the z component is less than 0. We've set up our dipole so it's pointing in the z direction. So our force z component, mu z dbz dz, is negative, which means that when you put a dipole in this field above the ring, then it will experience a force downwards, and it's attracting the dipole into a greater field strength. Now, we can make a model for this, because remember, a current loop is like a magnet. So we could think of, this is the current loop. We're just approximating this as a magnet. Our dipole itself is another source north-south magnet. And when you put two magnets with opposite poles adjacent, then you expect a force on the upper magnet down. So this equation, in some sense, is explaining why magnets that are oriented with north-south, north-south attract. And if you flip this, the dipole moment would flip, they would repel. So here we have a qualitative explanation of why two magnets attract. The important point here is that B is non-uniform. That is the essential idea, and that's why we see it in the gradient. Remember, when B is uniform, the force on the dipole was 0, and you see it again in the fact that it's the gradient of mu dot B, which we had talked about as equal to minus the gradient of the potential energy associated with the dipole.